solar system and all that lies beyond.
Hello, and welcome to another edition of the 2023 Von Karman Lecture Series. I'm Nikki Wyrick with JPL's Office of Communications and Education, and I will be your host for our exciting topic this evening, Perseverance, 2 Years on Mars. On February 18th, 2021, the Perseverance Rover touched down at Jezero Crater, a region of Mars where the ancient environment may have been favorable for microbial life. Mounted on the rover's robotic arm, Sherlock uses cameras, spectrometers, and a laser to search for organics and minerals that have been altered by watery environments and may be signs of past microbial life. Joining us this evening as co-host is Sarah Marcotte. Sarah brings over 2 decades of experience inspiring learning in out-of-school environments. Currently a public engagement specialist with Mars for JPL, she works to connect learners of all ages to current scientific research in person and online through events, exhibits, and virtual experiences. Hiya, Sarah.
Hello, how are you, Nikki?
I am well. How are you this evening?
I'm doing well. So tonight I will be taking your questions in the chat. So if you are watching this webinar on LinkedIn, Facebook Live, or YouTube, make sure you put your questions in, and our social media team will be sending those over to me, and maybe your question will get asked and answered on air. Now, if you don't see a chat box, try refreshing your page or reloading your page, and a place for you to type in questions should appear. And Nikki, can I tell people about something really cool for this anniversary?
Absolutely, please do.
Cool. Okay. So we have collected some of our favorite things from our website into one place on our webpage. So on the homepage of the Mars program site, it's mars.nasa.gov/Mars 2020. We've collected some of our favorite experiences to celebrate this anniversary. So on this page, there's a whole bunch of links to other cool things on our site that use real data, and in some cases, some of the real tools that the mission teams use. Now, for example, we have a Mars photo booth, and you can get real pictures of Mars and add yourself or your best friend to an image of Mars. Or you can hear actual sounds recorded by the Perseverance Rover. First time ever in all the years we've been exploring Mars, we've never captured actual sounds. So you can hear those on that page, and you can see a location map of exactly where Perseverance and the Ingenuity helicopter are. So all these neat experiences wrapped up in this one page. It's called the Best of Perseverance page. And that's how I'm celebrating the anniversary this year.
Awesome. Thank you for sharing that with our viewers tonight, Sarah. So I just want to remind all of you out there, as always, if we do run into any technical difficulties or small failures tonight, we ask for your patience and please stick with us. We will get them out as soon as we possibly can. Now, a special treat for us, our speaker this evening is Dr. Sananda Sharma, an interdisciplinary scientist focusing on astrobiology research and currently supporting the Sherlock instrument on Perseverance. She aims to understand the limits of life and the detection of biosignatures in extreme and Martian environments. And she is particularly interested in spectroscopy and microscopy, pigments as possible biosignatures, and simulation of extreme environments. But she is also passionate about cross-disciplinary research to promote greater inclusion and understanding across fields and audiences. Hi, Sananda.
Hey there, thanks so much for having me. Hey Sarah, and hey Nikki.
Of course, thank you so much for joining us for this special celebration this evening. First off, can you tell us just a little bit about who you are and how you got to work on this project?
Yeah, for sure. So I am, as you mentioned, a postdoctoral fellow here at Jet Propulsion Laboratory, and I'm a member of the Mars 2020 mission science team. And my background is a little bit varied. I've done a lot of microbiology, neurobiology, and design and architecture, and now I focus on astrobiology, and that's the study of the origins, evolution, distribution, and possible future of life in the universe. And
Great. Go ahead.
Yeah, so I was going to say, so when I So as I said, my background's quite diverse, and I applied for this postdoc position to join Sherlock when I just saw it posted online. So the way that I got involved in it is I had read a lot about Sherlock because it seemed like a very interesting instrument that combines all of these unique capabilities and gathers all this different type of data that gives a wealth of information about rock surfaces. So I had never been to JPL or done an internship here, and a lot of folks who are postdocs have, but I didn't have the grades for it when I was an undergrad, and it took me a long time to figure out how I actually learn. And I learn by doing, and I've always been really hands-on with both research about science and art, and that's a big part of my job now. So I get to do a lot of hands-on work in lab and also with mission data as it comes down.
It's great that you found a place where you can integrate your passions and your love with your work and your study. So I'm glad you're here. But can you tell us, what has it been like these past 2 years working on Perseverance?
Yeah, so in a word, it's just thrilling. So we're exploring different regions of Jezero Crater, which is one part of Mars, and that's a crater that's 28 miles wide, and it's a little north of the Martian equator. And so there's evidence that this region was home to an ancient river delta, and there are a lot of minerals that were mapped both from orbit and things that we've seen from the rover to date that indicate that there was water there in the past. And it's possible that over 3.5 billion years ago, a lake existed here. And I think, so at this point now, we've completed our journey through the crater floor and the delta front, and now we're starting on the delta top. So next slide, please. Yeah, so this shows in this image, the white part shows the traverse, or where exactly the rover has gone so far. And so you can see we started in that crater floor area, and that has some of the oldest rocks that we would encounter, and it's rocks that we think were in place, so we don't think they were transported very much. And as we move through into the delta front area, we spent a good amount of time there, and we, as the instrument that I work on, Sherlock, we looked at 11 different targets that were there. And now we're just starting the Delta Top campaign, and I'm very excited about this one because we're going to see some things that possibly we haven't seen before to date on the traverse.
Very cool. So we've gotten an idea a little bit about what it's been like working on Perseverance the last couple of years. But can you tell us, what is Sherlock, the instrument that you work on?
Yeah, so Sherlock, if you can go to slide 5. Yeah, so Sherlock is, it's an acronym like many things that are here at JPL. It stands for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. And it's one of the 7 scientific instruments that's on the Perseverance rover, and it's on the rover arm. So you can see it's on that right side all circled there. And that arm does a lot of work. So it does our proximity science, meaning it observes rocks really up close, where some of the instruments are remote science instruments and they work from a little bit further away from a rock surface. So Sherlock is a deep UV, Raman, and fluorescence spectrometer with 2 different imaging systems, and one of them is called Watson, so Sherlock and Watson. So when I said that it observes rock surfaces up close, I mean literally imagine the height of a credit card. That's how far we are from rock surfaces, so 48 millimeters away. And Sherlock gives multiple different types of information. So it gives image information and spectra. And spectra are basically signals that result from light interaction with a rock surface. And the light that we use is a special type of laser that you can think of as sort of a fancy black light. And it helps us see things that are in the rock that would be otherwise invisible to us. So the images that we take with Sherlock's 2 cameras, that provides visual context for where the laser hit. So when Sherlock studies a rock surface, it shoots its laser in a pattern across an area that's about the size of a pencil eraser, so quite small, and it lights up different components in the rock, including chemicals, minerals, and organic matter. And organic matter, or organics, as people sometimes say, that is made up of the element carbon. That's along with other elements like hydrogen, nitrogen, and oxygen. And organics are super interesting to us because they're commonly called the building blocks of life. So all life as we know it is made up of organics, but organics, importantly, can also be made through other chemical processes, such as through water-rock interactions, and it's also found in interstellar dust. So with this 2 types of spectroscopy, Sherlock helps the rover detect different spatial patterns of organics and minerals and give important views of samples that we're seeing with minimal alteration. So we go up to a rock, the only things that we would do is either blow dust off the surface, or abrade, meaning remove the top layer with a particular drill bit that we have, and then just observe the rock in place, so no busting it up or anything like that.
So that's a great description of Sherlock, but why would we want to have something like Sherlock on the rover?
Yeah, so let's put it into context. So if you go to slide 7, actually the one after this, I think, or yeah, this one, exactly, perfect. So all of the instruments that we have work together on the rover quite elegantly, and across all of them we can get chemical, mineralogical, elemental, textural, color, and stratigraphic data to catalog all the most detailed information possible across spatial scales and across observational axes. So Sherlock, as you can see, is on like the finer scale, so on the right side of the slide that's here. So we work on the centimeter all the way down past the millimeter scale. So we have some of the closest views that we've had to date of rocks on the Martian surface. And Sherlock is the first of its kind instrument that's operating on Mars, and it gives us especially important information about rocks that are, as they're found, to support the selection of samples for return to Earth. And that's for potential return to Earth. And that's one part of this mission that's particularly interesting. So previously, when we've gone to Mars, we're trying to get all the information that we can from the surface. And in this case, what we're doing is there's a potential opportunity for us to return samples back to Earth for further study. And so what we want to do with the instruments on the rover is collect all the data possible so we can decide, make almost a priority list. We observe something here. Does that look like a sample we'd want to bring back to Earth and do further study on? If yes, collect. And that's something that Sherlock helps a lot with. So it's able to look at all those different components in a rock and figure out, are these say minerals that could preserve organic matter or potential signs of life really well, then we definitely want to put that at the top of our list to return. So it helps with that sort of in situ, meaning in place, information gathering.
So you talked about all the benefits of this, but how do you tell what you're specifically looking for? How do you find those things?
So I think it depends on who you are and exactly what you're looking for with that. So I would say, can you go back to the video that was before this? Yeah, exactly. So this is an abraded patch called Guillaume, and I'll use it as sort of an example here. So this is all the different views that one of the Sherlock cameras has that you're going close to it. And if you're a geologist on the team versus a mineralogist versus an astrobiologist or a microbiologist, you're going to say you're looking for something specifically different. But here you can see kind of a wealth of everything that all of us get to see. So some people search for signs of a particular mineral. So those white patches that are right in the middle might pop out to them, like say, okay, that's quite interesting. What does that look like? And in terms of Sherlock data, we would scan a particular part of this abraded patch, and the signs will show up as peaks within our spectra. And that we can match that pattern of peaks to standard reference libraries that we have built here on Earth to classify the substance. And so for me personally, I look for particular types of minerals, so particular spectra that match with minerals from reference libraries that we have that are really good at preserving organic matter, because that's what I'm interested in as an astrobiologist. So can you go to slide 9, please? Yeah, so I think this is a nice demonstration of literally what Sherlock does. And this is one of my favorite examples. It's from its abrasion patch called Cartier, and it's literally like my phone background because I like it so much. So this is we found this beautiful white sulfate patch. So sulfate is a particular type of mineral that's known on Earth to preserve some it can preserve organic matter and also potentially biosignatures. And so this one popped out really clearly on this rock surface, and it's also in the shape of a polar bear. So that's also why we were so excited about it. So this is the knee of the polar bear that's being scanned. And so on the right side, you can see the scan map of Sherlock, which is going over that pencil eraser size area of the abraded patch. And it moves through point by point through 100 different points on this scan. And at each point, we're collecting spectra, and that's what you're seeing on the left. So all of these squiggly lines, that's actual information. So the position and the shape of the bumps that you see in that spectra, that's what we're trying to interpret. And so on the left side, you can see how that spectrum changes as you move point to point. So you analyze all the peaks that show up there and then start asking, what material could yield this signal? Why is the signal in this particular place, and what does that match up with? How strong is the signal? What sort of colors or textures in the rock is it associated to? And if we were just scanning without mapping, figuring out which signal comes from which part of the rock would be way more difficult. So here, this was a sulfate, as I mentioned, and that has that big peak that's closer to the left side of the spectrum. And then we also see something that looks like hydration. So that bigger bump that you start seeing on the right side of the spectrum, that's an indication that this mineral has some water that's stored in its structure as well.
It's incredible to think of the things that Sherlock can show us and tell us. We're going to come back for a few more questions and continue our conversation in just a second, but I do want to open it up. We've had a ton of questions online tonight, so we're actually going to let the audience ask the next 2 or 3 questions. Sarah, what are they asking out there?
Okay, so a lot of questions are coming in, and I'm having trouble deciding. However, I liked this one. Of many I like. So Esmo on Instagram asked, what is your number one hope for what we find or discover from the samples?
Ooh, good question. Also, very difficult question. Everything's very exciting. Okay, so I think the answer, what I think about the most when I think about what I would want to see is diversity. So what's a win to me is when everything doesn't look the same, because that means we're getting the most that we can out of this trip to Mars, and we're hopefully getting the most of the samples that we get back. So basically, I want to see not just one set of spectra associated with one texture and one mineral. I want to see all these different patterns popping out. And that's actually the most exciting thing I've seen so far, is some of the work that I did is to do the comparison of what mineral we're seeing with what sorts of other signals. And we're seeing a huge diversity across that. So I think that's the biggest dream, is that we capture the diversity that Mars has, because I think we're almost, on Earth, we think so often of like, oh, I can think of 10 different types of ecosystems and environments. And then you look at pictures of Mars and you can say like, actually, if you go to slide 3, you can see what yeah, exactly. So when you look at this, you might think like, all that stuff looks the same. Especially if you haven't been spending a lot of time looking at Martian rods, you can say, hey, all that looks the same. Why does it matter? But then when you take all the scientific instruments that we have on the rover and you look way more closely at it, then you realize there's so much diversity that's hidden right behind there. So capturing that, I think, is the most important and exciting thing.
All right, how about another one? So Udaya on Facebook asks, what if signs of life are not found on the surface? Would the subsurface be scanned for life also?
That's a great question. And yes, there are other potential missions that are being proposed that would be looking at the subsurface instead. And that question, I think, gets to the heart of one thing that we're all a little bit, that we all go into this field aware of, which is the surface of Mars is not a really happy environment for life as we know it. It's pretty harsh because there's things like UV and ionizing radiation that are all hitting the surface. So anything that lives there would have to survive under all of those conditions. And it might be that life says, hey, this is too harsh up here. We have to go down to the subsurface. And it might be in the subsurface. So yeah, we're appropriately sort of, I think, tuning our expectations that we might not find all the signs of life on the surface, but maybe future missions can go below the surface.
Should we do one more, Nikki?
Absolutely,
All right.
please.
Sure, let's do it. So Ivana on YouTube is asking, so Sunanda, you consider yourself an astrobiologist. What are some topics that an astrobiologist could research on Mars?
Ooh, okay. So I think...
Do we have all night? No, kidding.
I know, right? All night and all day, I want to say. A lot of different topics. So I think one thing, so there's a couple of different categories that I think an astrobiologist could look at. So one thing is biosignature. So do we see anything that could be a potential biosignature? So a potential sign of life, meaning a pattern, substance, or other sort of compound that would require life for it to be created. So with the tools that we have on the rover right now, we can say that we could potentially find what we're calling potential biosignatures, meaning that these are really interesting, we should bring them back and then decide whether it's a true biosignature or not. So that's what we can do with the rover, and that's one area that I think an astrobiologist could work on. Another area is looking for signs of habitability. So on Earth, when we think of what would make a good environment for life to thrive in, you think about like water should be present and abundant. Ideally, we won't be at the extremes of pH because then it will be a sort of milder environment. Ideally, there wouldn't be an insane amount of UV or ionizing radiation, so life would be able to thrive there. So finding key signals, so particular mineral assemblages or things like hydration, that can help build the story for what is habitability. So I think those are two areas that an astrobiologist could work on. And then there's a lot more too, just two examples.
That's some great advice. Keep asking your questions out there. We are going to come back for more, but I've got just a few more questions for our wonderful speaker this evening. So you've been with Perseverance and it's been on Mars for 2 years, and you touched on this briefly, but what is one of the most interesting things that you have found from Perseverance?
Okay. So I think, okay, so I kind of answered this earlier in terms of looking at like the diversity, but for me, so first, every time we get data down, I like to get to it as soon as possible. So one of my colleagues who's an engineer and in operations will say, hey, the data set is ready, and I'll immediately download it as soon as I can. And the first thing I do is I usually flip through all of the spectra and images that we have, and I try to see, does this look like anything we've seen before, or does this look totally different than what we've seen before? And when I'm going through all the different spectra as they come up, I try to categorize all the different groups that I would see. So I see a particular peak in this place, or I see a doublet-shaped peak here. What does that mean? And then I try to sort of build out all the diversity and then match it to each type of texture that we see, and then matching spectra of Raman and fluorescence each together. So I think what I personally have seen that's the most exciting is we're seeing clusters, I would say, of particular minerals with particular fluorescence signatures. So that's one of the types of spectra that we collect. So with Raman, we're getting some mineral information, and with fluorescence, we're getting a different type of spectral information. And what it looks like is it isn't everything is matched with everything. There's particular trends that we're starting to pick out, and we can only start to do that now. So this image that you're seeing is in the crater floor, and if you go to the next slide, this was taken as we were moving into the delta front area. And so to me, what it's looking like from all of these trends is that the crater floor and the delta front don't look the same. And we're seeing sort of hints of this mineral fluorescence association as we're moving through the entire traverse of the rover. And I think now we're finally at the point that we can look back and say, Sherlock has seen 21 different targets so far. What are the bigger picture stories that are showing up here? Why aren't we seeing the same thing everywhere? So yeah.
Well, that's great. So now we've got this bigger picture idea from Perseverance, but what's next for Perseverance, both in the immediate and the further out future for this rover?
So I think we're on Sol 709. Yes, I think so. And so as I mentioned, we just wrapped up the Delta Front campaign. And now the campaign science leads and the team overall have planned an excellent Delta Top campaign that we're just starting. So I sort of hinted at this, that there's some minerals that maybe we haven't seen in such high quantities that hopefully we'll encounter during this traverse. So I'll say the short term is I hope to see something like hydrated silica. And that's a type of mineral that can, on Earth, it can preserve signs of life and organic matter really well. So that's short term, something that I'm looking forward to. Medium term, as we move out, like maybe a year from now, if everything goes awesomely, we're going to encounter minerals that are called carbonates. And these were mapped from orbit like years and years ago. And I've been hearing about them literally all through my PhD. I've been hearing about the marginal carbonates and how they would have a lot of promise for preserving biosignatures or signs of life. And these are in the western inner margin of the crater. Carbonates are minerals that are found in a lot of things on Earth, like in limestone, in shells, in hard corals. And they're also found in a bunch of different rocks that aren't related to life either. But they are great preservers, as I mentioned, of biosignatures. So if we encounter that, I think we could find some really exciting things there. And then long term, we're excited about the potential Mars sample return campaign. So as I mentioned, we collected a bunch of different samples so far. So we got 9 that were in the crater floor of rocks, and then 9 rock samples that were from the delta. And if we can get those samples back to Earth, we're going to get a whole new set of laboratory data to augment what we learned from the rover itself on Mars. So I'm really excited about the potential of Mars sample return and how much more information we're going to get, because there's so many tools that I think all of us wish we had, but it's not feasible to miniaturize them and make them super robust and send them on a rover. So when we get these samples back to Earth, we'll be able to do all of those like high resolution analyses with, equipment that's the size of a room, and we'll be able to get all of this information down to probably even the nanometer scale. So hopefully if we get them back, and if I'm able to do everything I need to do to keep working in this field, then I hope to be lucky enough to work on them.
Well, I think it's just incredible to think about how much this rover and Sherlock have done in 2 years. I mean, we are incredibly excited about the future of this mission and what it's already been able to accomplish. So I actually want to turn it back over to Sarah, because I know the audience has asked you a ton of questions online. So Sarah, what else are they asking out there?
All right, let's look at the question box here. So Rosetta on YouTube asks, what is the most surprising thing we've learned so far from Perseverance's explorations?
Ooh, that's probably also going to be a question that varies based on who you ask, so I'll answer for me. So I think, let me see, what's most surprising? I feel like there's a lot of surprising things. So, okay, there's one particular signal that we've been having a lot of conversation about within the team, and it could be a couple of different things. And we're literally pushing the boundaries of what we know so far with fluorescence spectroscopy and with Raman spectroscopy to figure out what this signal could be. So it's a signal that we saw sort of hints of in the crater floor at a couple of points in one rock that was there. And then as we moved to the delta front, we started seeing it more and more. And we're still seeing it now as we're like making the transition into the delta front. And I'm curious if we'll still see it in the delta front. But yeah, that particular signal literally keeps me up at night. It's like a doublet at 3:03 and 3:25, and I'm trying to think more and more about it. So I think that's a really surprising one that I don't know exactly what that is, and I'm hoping that we're able to get these samples back so we can actually do the full characterization. So I'd say that one was surprising and exciting for me.
All right, I'd say I have kind of a related question to that then. Travis on LinkedIn is wondering, are you finding minerals and signatures not currently mapped to Earth's known minerals? And if so, what's next?
That's a good question. I think a geologist could give you a more specific answer. From what I understand so far and all the matching that I've done with minerals, they're mapped to our reference library. So we can say like, okay, we classify this mineral as a sulfate or a carbonate or a silicate or something like that. That being said, not all of them match exactly perfectly. And this is where it starts to get into sort of an interesting gray zone, which is the instruments on the rover have their own limitations, right? So we might not be seeing everything in exactly the perfect spectral resolution that we need in order to identify a specific mineral. So there's a little bit of like a gray zone there. So not everything will fit exactly perfectly, and that's part of why we need the samples back. But I would say largely we're seeing what we expect to see based on the reference libraries that we have. So we're able to do matches in most of the cases.
Now we've had a couple questions sort of in a row that are somewhat related to this, and this is funny. I think I have heard this question before, but Billy on Facebook and Arnie on YouTube asked a similar question, which is about precious metals. Have we found anything like gold and silver on Mars?
Interesting. Not that I've heard of. We can check with all the geologists on the team. But the things that I'm hearing, and I guess maybe it's because of my lens as an astrobiologist, the astrobiologist gold is minerals that preserve organics really, really well. So for me, I'm like, well, my gold is a sulfate or my gold is a hydrated silica, and that's why I'm so excited for the delta top. But yeah, I would say like I don't really know the exact amounts that we would be expecting to see on Mars, but everything that I've heard so far is these types of rocks that we know, or these types of minerals that we know are in igneous rocks from our studies on like Martian meteorites and from previous observations.
All right, let's hear from Violet on Instagram, who's asking, does Perseverance itself have tools to analyze samples, or can they only be analyzed on Earth?
Good question. So those 7 scientific instruments that I mentioned, we do analyze the rocks as we're finding them with those. And so what we do is when I mentioned those abrasion patches, that's sort of like a proxy for the actual sample, the rock sample that we pick up. So what we do is we use those instruments to observe right next to where the sample is picked up, so we have a good understanding of what hopefully we're actually picking up. But those actual samples that are put in the tubes themselves, those will be fully analyzed when we bring them back. So I would say the instruments on the rover do a lot of analysis and they collect a lot of data, and that is directly applicable to the samples that we're hopefully bringing back.
I have another one. This is a cool one, like from an astrobiology perspective. So Sherry on YouTube is wondering, how do you make sure that you're not concentrating on finding evidence of life that it would look like as we know it here on Earth, and that science might miss life on Mars?
Thanks for this question. I love thinking about it, actually.
I know, is that a good astrobiology connection?
That's such a good one, yes.
Yeah.
So I would say, so we have working hypotheses for what the definition of, or a working definition, I should say, of what life is. And we're guided largely by what we know about life on Earth, because that's the only example that we have of a planet that hosts life. So we're definitely limited by that. And I think that's where having sort of the agnostic approach and being able to clearly say, like, we are designed to detect life as we know it. And there could be other signs that we are missing. That's always a possibility. And I think anyone who's in astrobiology gets, they're both aware of that as like a limitation of our knowledge, but also incredibly excited, because that has started this whole other part of the field in astrobiology of looking for agnostic biosignatures. So say we're not looking for exactly the types of elements, like all the things that I just mentioned about organics. What if we're not looking for that? What else could life present as? And what is a reasonable thing to search for? So this is a newer part of astrobiology that's still developing.
All right. Let's see. This is kind of a personal one for you, Sunanda. Rachie on Instagram is asking, what part of this mission has been your favorite or most memorable?
Ooh, okay. Aside from the polar bear, because that was of course the polar bear was excellent. It is my phone background, and like part of the other reason that one's so exciting, just for a second because you asked, is at one of those particular points, like one of the spots that we analyzed with Sherlock, we saw signs of multiple different minerals all together, and a lot of times we just see like a single mineral visible through Raman. So that was really exciting. And then I would say like that's good. And then another thing would be, I would say the first time that I actually got to analyze the data myself, because I came in when the mission had already started. So I came in right around Guillaume. So the first time I looked at that data, it was sort of like, I'm still learning what's going on. I have no clear idea of what all this means, and I'm still doing background reading and all that sort of stuff. But then the next target, Bellegarde, that was the first time that I was like, okay, this data's coming down and I'm going to look at it myself. And I literally printed out every single picture that we got, which was a lot because we take a lot of pictures with Sherlock and with all the other cameras. I think we have over 20 cameras on the rover. I printed out every single picture of the rock, the outcrop, that particular patch, and I put them all up in my office, and then I looked through every single point. And for me, that was like a personal exploration, and also just so incredibly exciting that I had all of this information of Mars just staring at me in my office. So that, I would say.
Okay, this is one that's tugging on my heartstrings. So Mindy on YouTube is wondering, her 3-year-old wants to know if Perseverance will go visit Opportunity. His new favorite thing is watching rover documentaries.
Oh, that's great. Oh, so maybe in spirit, but in practicality, I don't think so. And I think part of it is that like we're exploring a different place, but maybe one thing that would give you comfort is that all of the information from all the previous rovers and this one, this is all coming into one big picture of our understanding of Mars. So all of that information will get put together, and we're building on the legacy of all of those previous sorts of explorations. So we have our plan, and we're going to go through exactly where we've planned in our traverse, but keeping all of that previous work in mind.
Yep, so opportunity might be gone, but certainly not forgotten. And as you mentioned, that Perseverance is standing on the shoulders of the rovers that came before it.
Yeah.
So, Sarah, I think we've got time for one last question from the audience.
Sounds great. Okay, I have one to bring it home. And this is from Reishi on Instagram saying, what advice do you have, Sunanda, for someone interested in the STEM field?
Ooh, okay. I would say that I think there's a lot of emphasis put on like specific paths to get into STEM and make particular progress to like become a scientist in this way or an engineer in this way or things like that. And my advice would be to find your own path because for me, that took a lot of time. I did great in high school and then in college, I just had a really, really hard time. And I took all the science and math classes and all that kind of stuff, and it just wasn't clicking for me. And I had really bad grades until I started to figure out, like, what do I need to do to learn? And for me, it was research. I needed to be in a lab and finding out new things and thinking creatively. And so that's how I was able to reconcile the art that I did and the music that I played and the design that I wanted to do with the science that I wanted to do, is doing creative research. So for me, that was a path towards STEM. And I would always say like STEM plus art is incredible. That's what I always love to do. So don't be restrictive about how you want to approach STEM. Make it work for you because you deserve to be in the field if you want to be there. That's it.
And if I could add, you've worked on Perseverance. You've been able to do all these incredible things with Sherlock because you've had the perseverance to do them. And so that's some great advice to really persevere to our audience. Unfortunately, folks, that is all the time we have for this evening. I want to take a moment to thank our speaker, Dr. Sananda Sharma, for joining us to discuss 2 years of Perseverance. I also want to thank our wonderful questions co-host, Sarah Marcotte, and everyone working behind the scenes to make this possible. Make sure you check out the link Sarah mentioned earlier to get more information about the 2 years of Perseverance. That link again is mars.nasa.gov/Mars 2020. To all of you watching, thank you for taking the time to join us every month. If you missed one or would like to revisit any of our Von Karman talks from the past 5 years, they are all available on JPL's YouTube page. And please be sure to join us next month for Exploring Ocean Worlds with Eels, Exobiology Extant Life Surveyor. That's all for tonight, folks. Thanks, and bye, everyone. Have a great night.